Hello again, this is the Pentecrest High School AP Physics 1 video series. This is video 6G, Mechanical Explosions. Alright, first of all, let's get this out of the way. Mechanical explosions are not as much fun as you think they're going to be. Mechanical explosion is the rapid transfer of potential energy into kinetic energy, typically from a spring. It could also come from stored chemical energy like an explosive charge that separates solid fuel rocket boosters from a rocket or a space shuttle. So it's not this kind of explosion, it's a mechanical explosion. So we're going to begin with the premise that momentum is conserved. So P equals P prime, that's been our guiding premise since the very beginning. First of all, our easiest one-dimensional explosion is one in which the objects are initially at rest. Consider two carts butted up against each other as shown. One of the carts has a spring-loaded plunger in it. You can see M1 has the plunger inside. Now, initially, what's the momentum of the system? Neither of the carts is moving, so the system momentum is zero. That's going to be critically important later on. Now, when we depress the button and the plunger pops out, the carts are going to move away from each other in opposite directions. That's the explosion, is that rapid release of energy. You can see we have M1 moving at V1 prime after the explosion, M2 is moving at V2 prime after the explosion. So each of the carts has a momentum after the collision, but the system momentum has to stay the same. So according to this diagram and this arrangement, M2 V2 prime is to the right and M1 V1 prime is to the left. What can you say about the magnitude of each cart's momentum after the explosion, given that you know momentum is conserved? Now, if the objects are at rest before the explosion, initial momentum is zero, and then these represent the momentum of each of the carts afterwards. Notice that we have vector symbols over each one. Now for this particular situation, M2 V2 prime is to the right, M1 V1 prime is to the left, so we're going to use our standard sign conventions, and we would say that 0 equals M2's momentum after minus M1's momentum after, or the two momentums are equal. Now, what if the combined mass is moving before the explosion? We're going to adapt P equals P prime to this situation. The system now has momentum before the explosion. It looks quite a bit like a completely inelastic collision, but in reverse. So initially here, we have a combined mass M1 plus M2 times an initial velocity v. And then afterwards we have independent M1 V1 prime, M2 V2 prime. Again, the momentum stays the same. Make a note of the vector symbols. The directions matter. We don't know about V1 prime and V2 prime in terms of what directions they are. Depends on the amount of kinetic energy that's released. We would typically have to know one of the two. And typically use the equation to solve for the other one. Another way that a mechanical explosion is like a completely inelastic collision in reverse is that there's more kinetic energy in the system after the explosion than there was before. So momentum is conserved, but kinetic energy is not. Instead of decreasing like it does in a collision, in a mechanical explosion, the energy in the system increases. Now we're going to extend this idea into two-dimensional space. So if you can, consider a stationary mass that blows apart into three separate pieces without any loss of mass. So we have this object sitting at the origin. It's going to blow apart into M1, M2, and M3, which will then fly off in different directions with different velocities. So the system momentum before the explosion has to be 0, and that means the system momentum after the explosion also has to be 0. As before, when we looked at X and Y directions in a two-dimensional collision, we have to treat the X and Y directions independently. So again, we're going to use a table, and you can see as before we have X and Y, rows for X and Y, and columns for before and after. Before the explosion, the momentum in the system is 0, so both of these components, X and Y, are both 0. And then afterwards, again, each piece has a momentum vector associated with its velocity, and each one of those has an X and a Y component. There's M1's X and Y, M2's X and Y, M3's X and Y. Based on the image, you'd be able to make a prediction in terms of the signs on each of the components, to the right and up, left and up, right and down, based on which quadrant they're in. Now again, before equals after, so each of those crazy expressions on the right in the after column has to equal 0. In other words, all of the X direction momentum components have to cancel out. All of the Y direction momentum components have to cancel out. We typically would have 2 of the 3 velocity vectors and the masses of each piece. We would probably have to solve for the third piece's velocity, magnitude, and direction. For the sake of this demonstration, we'll say that we don't have V1 prime or beta 1 prime. We don't know the momentum of this piece after the explosion. So again, we set Px equals Px prime, Py equals Py prime. We set the 0 equal to this, 0 equal to this. And what we're going to do is isolate the terms that are associated with the piece that we don't have. So we don't have V1 prime or beta 1 prime. We're going to rearrange these, put the piece that we don't have, the X component of M1's momentum after, and the Y component of M1's momentum after. Isolate those, and then we're going to try to find, we're going to use these to find the angle, realizing once again that these are vector components of M1's momentum after. So we're going to divide, as we did before. We're going to take the Y direction equation, divide by the X direction equation. We can eliminate M1 and V1 prime from this side, and we get sine over cosine, which is tangent, and equals the rest of this, which presumably is all data. So again, this whole right side, this whole mess on the right, is all numbers. So we can reduce it to tangent, do an inverse tangent function, get the angle, and then put it back in to get the velocity. Okay, that'll do it for explosions. That's it for impulse and momentum. Next up is rotation. Until then, enjoy, and I'll see you again next time.